Hello everyone. So today we'll be discussing another problem in our dynamic programming series, and this is called coin change. So let's go through the question. You are given an integer array called coins, representing coins of different denominations. Okay, means every number is unique, and an integer amount representing a total amount of money, means another target. Okay, there is two input, one is coins array and another is a target. Return the fewest number of coins that you need to make of that amount. If that amount of money can't be made by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coins. Okay, so we can pick a particular coin as many times as we want. So this is a knapsack problem where we can take a coin or we can ignore a coin, include or exclude condition. Plus, since we can take a coin infinite number of time, it's a unbounded knapsack. So first we're gonna create the decision tree for our knapsack problem and how we're gonna do it, and then we're gonna solve the same problem using a different decision tree, and that we're gonna solve using our dynamic programming. So let's see what happens in our knapsack case. So the example says that we are given a coins like 1, 2 and 5. Okay, and the target amount is 11. So now in this particular case, if we take 11, and we can pick either 1, either 2 and or 5, right? Now if we pick 1, the rest amount will be target -1, that is 10. Here target -2 is 9, and here 6. But after taking 1, again we can take 1, 2 or 5. The same goes to here, 1 to 5 and 1 to 5 and so on. And at the end we'll get at one point we'll get target equal to 0. If we get target equal to 0, then we have to return count. Means because we are not calculating here the path, but the number of number of coins. So every time we consider a coin, we have to add 1. So this will be like 1 plus 1 plus 1, and we're going to return the count. Same goes to here. For example, let we implement 6, then again we put 5 here, then remain 1, again we do 5, then target become less than 0. If target becomes less than 0, for that particular condition we have to return 0. Same way for every condition where we target it becomes 0, when you return count, we have to calculate mean of those counts, because the question asks for fewer counts, and that will be our answer. So let's try to implement this using the knapsack JavaScript solution. So first we have to, let's create another problem, function calc coins, and this will take our nums, then target, then I, and it will take our count. Okay, for our first base case, like base cases, you see if target is equals to 0, it means we get the sum, then we have to return the count. If target is less than 0 or I became greater than equals to nums dot length return infinity. I'm returning here infinity because we have to calculate mean. If it did not ask to calculate the mean, we would return just 0. Now we have to write our exclude condition, right? If target is less than nums of I, then we have to return calc coins nums. There will be no change in our target, then I plus 1 because we're going to exclude that particular coin, and there will be no change in count as well. Else we have to return math.mean of the exclude condition and include condition. In that case, the exclude condition will be the same, like calc coins, we're going to be target, sorry, nums target I plus 1 and count. And now if you include like calc coins, it will be like nums target minus nums of I, and it will be I because we will be considering the same coin multiple times, so we're not gonna increase the I, and then we're gonna do count plus 1. So at the end we have to calc. Now let result equals to calc coins. We're gonna put coins, then we're gonna put amount as target, and then 0 and then 0, and return result. So this will fail for certain cases, but we'll see. Okay, now past fewest number recursion. So yeah, so as you see that when it is returning infinity, because what happens, we are returning infinity, and when it failed, right, another one failed, so means there is no solution. It calculates the minimum and and so whatever present there just returns that like infinity. In that particular case, we have to check for that case, like equals to infinity, then return -1 or return result. So this would solve our case. So every test case has passed. So this particular condition is needed because of that condition that it says us returning -1 if it's not present. If the solution like says that if we can assume that if there is a solution always present, then we don't have to deal with this, right? Okay, now let's go ahead and see how we can do the same. We can solve the same problem using dynamic programming. So let's again go to our whiteboard and let's try to draw our decision tree. Now for the same problem, we have coins 1, 2 and 5, and target is 11. So now in dynamic programming, we had to use the numbers that we calculated before. So if we calculate sum for 11, we also can calculate the sum for 0, then how many coins needed to calculate 1, how many coins needed to calculate the target 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11, right? So we're gonna start from 0 and we can calculate 11, and by the time we reach 11 we can just use the previously calculated values to derive our solution. So let's try how we're going to do it. So for calculating 0, can we use 1? No. Can you use 2? No. Can you use 5? So for 0, this value will become, let's create our DP here. Let's create the DP, right? So can we calculate 0 using 1? No. Can you calculate 0 using 2? No. Can we calculate 0 using 5? No. So this will be 0. Now let's go to 1. Can you calculate 1? Yes. So 1 minus 1 is equal to 0. So we have 1 coin. You cannot calculate 2. You cannot calculate 5 because this is less than 2 and 5. Now let's go to 2. What's gonna happen for 2? Can you use 1? Yes. So we can use 1. So 1 coin. Then remainder is equal to 2 minus 1 equals to 1. Did we calculate for the target 1 before? So yes. So dp plus 1, dp for 1 is already we calculated 1. So total will become this one plus 1 equals 2. Now can we calculate using 2? Yes. So 2 minus 2 equal to 0. So there is only 1 coin needed. So can you use 5? No. So what is the minimum between 2 and 1? That is 1. So we can use 1. Now let's go for 3. For 3, can you use 1? Yes. So 3 minus 1 equals to 2. We calculated of 2. What is that? 1. So total coin is equal to 1 plus 1. 1 plus 1 equals to 2. Can we calculate 2 using 3 using 2? Yes. So that is 1 coin. Then 3 minus 2 equals to 1. How many coin we need to do 1? We can go back and see that is 1 coin. So total equals to 2. 5 we cannot consider. The minimum of 2 and 2 equals to 2. And the same way we're going to keep calculating till 11. Okay, and we're going to return the final number that is at the end of that array. Whatever number we calculated here, we'll be returning that. But there is a catch, because we will be returning -1 when there is no number. So we have to tweak this number, because this is the proper solution, but it will not gonna work for -1. So by default we will give it infinity, so that when we calculate minimum, if the number present, it will work. But if our result at the end become infinity, we have to return -1. Same way we did with the recursion. So let's try to do it. So now solve this using our DP. So first of all, in our DP we know that the first condition will be amount. If amount equals to 0, then we just have to return 0. We don't have to calculate anything. Then we have to create our DP. To create the DP, and that is like let DP equals to array of amount plus 1, so that the last index will become 11, and we're gonna fill it with 0. Now we have to iterate for every element of the DP, that is like let's for a is like I, then dp dot length, and dp dot I is the, don't have to dp dot I here, we have to the remain the target but every target is I, not dp dot I. So every index we will be considering as a target. And now we have to initiate every dp with infinity before calculating, because we have to return the minimum. Now we have to apply every coin for the particular target. So let's do it like again another for loop, and then you're gonna put j coins, and then we're gonna be coin. So every coin we're gonna choose. So once the coin is there, we have to see if coin is greater than target, right? Then we just have to do nothing. Or if target equals to 0, then our dp of I equals to 0, and we don't have to do anything. Because when the target is 0, we don't definitely the result will be 0, not infinity. And now we have to calculate the remainder. Let remainder is target minus coin, right? So every I is a target, then we reduce the coin from there, and then we will be if the dp of remainder not equals to infinity, then we have to do is dp of I equals to math.mean of I and 1 plus dp of remainder. Yes. So at the end, let result equals to our end, the last one, like dp of amount. This is the one. But again, if our array does not contains the result, it will return infinity. If the target amount cannot be calculated, it will return infinity. So we have to, same way as in recursion solution, we have to do the same check. Result equals to infinity, then return -1, else return result. So this should solve our problem. Let's see. And recursion is fine. You're gonna run this one. Coin. Okay. To get the point, this condition we have to put second. Wow. Sorry, now we get some syntax issues. It can be dp, and yeah. Now let's go here, and now I can run it. Boom, finally. So yeah, that's how we solve. I introduced a bug by mistake because of this code, but we can get rid of this bug by making it zero. We're gonna doing it zero, right? So we don't have to add this particular condition here. We're gonna take it out and we're gonna start it from 1. So it will ignore the first element, and this should work too. Now if you go here and run it again, it passed. Good. So this is how we're going to solve this DP, guys, and definitely we get introduced some bug and we debugged it. So yeah, thank you.